Okay, so we let me recap a little bit to remind you guys where we are so far. So we have uh pretty much done all three deliverables of project one, and project one is about credibility score. And what that means is you're talking to a chatbot, and then they give you back something like reference, and then you have a way of evaluating how good the reference is, how good the source is. Um, and then what we practice is this iterative development, right? Every deliverable, we're making a baby step. We're making an improvement. Like first deliverable, we asked ChatGPT, what is the function going to look like? ChatGPT said, okay, here's 5 API calls you can do. Great, let's do that. That's first deliverable. Second deliverable is let's package it together. That's what a class object is for. So we also did that. And then um, we look at the class object, we say, hey, look, there are a bunch of things you can do. You can build Streamlit application, you can get into the front end, get into a UI, do all sorts of cool things like that. But we don't trust it, right? So then we ask the class, okay, what do you rate this, right? So that's human in the feedback. That's human feedback in the loop. So we're practicing that process at a class level. So we ask class what the feedback is in terms of each rating, each URL, each prompt, you give a number, comparing with how many stars the function gives, right? And then we build a machine learning algorithm to try to reproduce that. So this is when the question happens. So some students email me, hey, how good of a performance does the machine need to be, right? Is it 70%, 80%, 90%? There isn't really a strict cutoff to give you a letter grade, say, oh, you have to hit 90%, otherwise it's not going to be an A. No, there isn't really anything like that. The reason that's the case is because you have to look at the nature of the problem, right? The nature of the problem is we provide a prompt and we provide a URL, and then there's a function rating and there's a human rating. So the machine learning algorithm is designed to take the prompt and then take the function rating to try to reproduce the human rating. If the performance is high, right, if the accuracy is high, that means the machine is able to make the guess of the human rating very close. That doesn't mean the machine is good. That just means the data is close to the rating of the function, right? It doesn't mean that you get 90%, therefore you are really, really good at this class. Does that make sense? Conversely speaking, if you get 50%, 60%, a very low accuracy, it doesn't mean you're failing this class either. Does that make sense? It just means that the machine that you train did not really know if there's a high relationship, is there a high association of the function rating and the human rating, right? So if you look at the nature of the problem, the accuracy doesn't mean how good you are as a data scientist. Does that make sense? Okay, so just want to throw that out there because there are some questions. So there's some students asking me like how good of accuracy do I have to get? No, there's nothing like that. So but that being said, obviously you want some feedback of how you're doing in this class. Fair. I'm gonna it will take some time for me to do this, but my plan is this. There are pretty much all the deliverables, all the weekly submissions, all the way to now. And then most of the deliverables, which means most of the submissions, is focusing on one project. So in the next 2 weeks, when you guys are on a break, I'm gonna in the next 2 weeks when you guys are on a break, I'm gonna take some time to pretty much compile the trajectory of the submission for every single student, and then you're not graded against everybody else, right? So there's no curve or no grade or no scale or anything like that. It's not like oh 5% must be A, 5% must be C, and everybody has to be in the middle. No, there's nothing like that. You are graded by your past performance. So you are graded by how you're doing in the previous deliverable, right? Because everybody is doing their own project. Does that make sense? So I'm gonna unpack that a little bit more, and then I'm gonna write out a feedback for every single students, so you know what to do, and then at least you get some feedback. It's gonna be a little bit different from other class. Most of the class that I taught in the past, there's gonna be like some sort of homework, right? Homework, there's true and false, right? You either get it right or you get it wrong. And then every homework you get a grade, something like that. So this class is a little bit different. The feedback is mostly going to be how you're doing and how you're iterating on your previous version of the function of the project. So any questions? Great. Okay, so yeah, with that being said, I'm gonna that's on me. I'm gonna get that out in the next 2 weeks. And then a couple of housekeeping item. Just to reiterate, right? Next week it's midterm, right? So there's no class. You're welcome to come here, but no one's gonna be here. So next week is midterm. The week after that is spring break. So there's no class for the next 2 weeks. Any questions? Okay, great. So next time I'll see you guys, it's the last week of this month. Make sense? Okay. Cool, awesome. So we're gonna get that out of the way, and then what that means in terms of what we're doing in this class is there's no deliverable, meaning that there's no submission for next 2 weeks. But today I'm gonna obviously give you guys something in regards to project 2, so that you guys can think about it. But it doesn't mean you have to submit anything. I mean, you're welcome to submit things before the last week of March if you want to. Obviously, I'll read it. But you're not responsible for submitting like anything next week. So any questions about that? Good. Okay. Awesome. So with that being said, let's dive into what we're gonna do today. So I'm hoping to achieve 2 goals. Let me share my screen so everyone you can see it. I'm hoping to achieve 2 things by the end of today. The first thing is to give you guys this concept called tiny troop, which is what we're going to do for project 2. Same structure as project 1. I'm going to set things up, and then there's 3 deliverables. Every deliverable, you're going to iterate on what you've done in the past. Make sense? So you're not like competing with each other, you're competing with yourself in the previous deliverable. So the first session, I'm going to talk a little bit about this project and what this project is doing. I think it's much more creative than the previous project, which is why I like this project. I'm going to set things up. I'm going to give you guys 2 versions. One is using a package, one is without using a package. So you get the idea of how to do both. So that's the first idea. The second thing I want to hope to achieve by the end of today is get you guys started on deep learning. So what I mean by that is right now, if I can take you to the slides, we've covered all the way to support vector machine. So that's what we all cover to chapter 9. And then what I'm hoping to achieve is from today, we're going to kickstart chapter 10. And then chapter 10 is a very long chapter because we're going to, there are a bunch of stuff in it. There's like neural network, which probably everybody already know. There's convolution neural network, there's a recurrent neural network, and there's generative AI after that. So this chapter is a big chapter. It's a much more condensed version of like the deep learning class. Conventionally speaking, this chapter should probably be broken up into 2 classes. One is neural network and convolutional neural network, and then another class it's like natural language processing, and then there's like another class after that. It's like the generative AI stuff. But I'm hoping to cover the famous algorithms within that entire topic, so you guys know a little bit of everything. So that's what we're gonna do for that's the second goal that we have today. Okay, so with that being said, let's get things started with tiny troop. So tiny troop, the idea comes from this. Microsoft has a package, literally it's called tiny troop, and if you just Google it, the first link should be it. So you click on that and you scroll down, and you can read about this giant paragraph. But essentially, the idea is this. This picture actually does a great job of showing you what the idea is. So tiny troop, the idea of tiny troop is we use large language model to simulate a different world, right? Different world, different conversations as a proxy of pretty much anything you do in business, right? For example, a product trying to talk to a customer, a salesperson trying to talk to a customer trying to talk to a customer support, data engineer trying to talk to the product manager, so product manager can know what data is in the company, all that sort of stuff can be simulated using this package, right? So on a high level, it's a software package that you can run in Python that helps you create these mini conversations, and you just hit a button and then it will just run for you. And then you have multiple people after certain persona, and you can customize the persona, and then the two people will talk to each other. So on a high level, that's what this package is doing. Of course, you can say, hey, I don't like this package. I'm gonna go on and do my own. Perfectly fine, perfectly normal. And I actually expect some of you to pull this off. Hopefully the maybe not this deliverable, but like deliverable 2 and 3. I'm gonna guess probably someone's gonna pull this off. Which is how do you reproduce this package completely on your own without using this package. So that's the idea. And then if you go down the list, there are like a couple of different ideas of the conversation that you can do. Like for example, advertisement trying to gather sales data, something like that. You can certainly pull that off using this package. Software testing. I think the idea here is if you have a new product coming out, like a new feature on your chatbot, and you want to gather customer feedback, and then you can have customer to interact with that feature a little bit in this mini world that you're building using this package. And then you can probably pull that off and get some customer feedback. There's a pros and cons about this. So if you use this package, the pros is you can very quickly build a small simulated conversation and get it going. And that's the pro, it's fast, right? The cons is throughout building it, you get a sense and you get a feeling that you can only do what the package tells you to do, right? Obviously, right? Because the package is designed to do that. Package is designed to do like 10 things. Then you can do 10 things. If you want to do the 11th thing that's not the 10 things, well then sorry, you can't use a package. Or you have to work your way around. Which is why this today's session, I'm gonna show you guys how to use this just as it is. And then next time we'll come back, I'll show you guys how to do this from scratch. Okay, so there are different ways to do this. Of course, you can install a bunch of things in your own computer. What I'm going to do today is a little bit different. What I'm going to do today is I'm going to try to do everything on the cloud, just so that I don't affect everything in my local computer. Because I have this happen in the past that some students install this and they're like, oh, I have to install like 10 other dependencies. And then they like screw up their computer. They have to like essentially reinstall Python. So I'm going to do this on the cloud. So hopefully give you a safe way to not affect your laptop, right? So if something goes wrong, you just turn that repo off or delete it, right? Okay, so let me get started. I'm gonna put it like, I'm gonna put it like this. Okay, so left-hand side is a tutorial. I'm gonna pull this code from left-hand side, and then I'm gonna do this on the right-hand side. Let me make sure this is a recording. Yeah, okay. So you create a new repo. I'm gonna call it tiny troop, and then this is I'll call it test1. You can write whatever description you want, leave it public. You can add a README file, which I'm gonna do that. Git ignore, it's not a package, so you can just ignore the git ignore. And then the license, again, it's not a package, so you just leave that as it is, create a repository. And then what I'm gonna do is go to code and open the code space. So what this is gonna do is it creates a Visual Studio IDE on the cloud that's backed by that repository. And it's as simple as that. And the benefit of that is give you a terminal. And I'm hoping to basically do that completely using a terminal. So now you are here. What's happening is first thing you're gonna do is you're gonna git clone this repository. So I'm gonna put that there. And then this is gonna pull everything from the Microsoft package to a local environment, and you see this little thing here. So everything is in there. So that's step number 1. Step number 2 is you cd into that folder. Cd means change directory. So once you're in there, you can do a pip install, and then you should be good to go. So this is gonna install the package using this artifact that you just downloaded, right? So it's a different concept than like pip install tiny troop, right? Which you can also do that. That's perfectly fine. So we're gonna give a little bit. Once it's done, all the dependencies should be there because it's a clean environment, it's a clean slate. So everything should be there. Once it's ready, you can essentially run through the rest of the step, which I'm gonna do in front of you guys. While I'm doing that, I'm gonna pull my API key. I'm gonna have to stop recording for just a sec. Don't want to show people the key. Okay, so now once you get your key in there, you can instantiate Python and you can pretty much run through the rest of the step. So that's my Python. And then first things first is let's pull an example, right? So from tinytroop.examples, import create Lisa, the data scientist. So this is a particular function that's a single persona that's built using this package. And this is just an example, so you can see what's going on. So once you pull this package, there's like a bunch of warning, you can just ignore that. First thing you need to do is use this function, right? This one, create Lisa the data scientist. You use that function to define an object. So I have sample code here. I'm just gonna copy paste here. So Lisa underscore ds, that's the object that we defined just now. And then you can see that the class object is tiny person. Okay. And then you can then talk to it. For example, you can say, hey, Lisa ds, please listen and react to what I'm about to say, right? And then what you're saying is, tell me about your life. Now, this conversation is going to start, and then this Lisa persona is then going to try to react to what you're talking about. So let me zoom in a little bit and just make sure everyone can see this. Okay, so what's happening here is this. Let me hide this. Okay, so what's happening here is this. The user said Lisa DS, it's a tiny person object. The tiny person object comes from the package. And then it carries this method called listen and act. And then you can throw in a string. That string can pretty much be whatever you want it to be. And in this case, I just want to know who this object is. So I ask you, hey, tell me about your life. And then this is the essentially a little bit of a chain of thoughts that's built into this package. So what I mean by that is the user is going to ask Lisa, hey, tell me about your life. So it starts a conversation. And then Lisa Carter, before she answers the question, she thinks about a little bit. The question about my life is quite broad. I should think about the key aspects to share, like my background, education, current job, things like that. And then after the thought process happened, and then Lisa is talking. So the interesting thing about here is the design is Lisa acts is like kind of like a method. And then there are different types of method. Think is one type, talk is another type. Does that make sense, the logic here? And then it's going to say something back. Sure, I grew up in Vancouver, Canada, in a tech-savvy family. My parents were software engineers, which inspired my interest in technology from a young age. So now you get the idea, right? So now this Lisa person is in your computer. She carries certain persona and she has a personality. And then if you talk to her, she'll respond back. So on a high level, you can kind of think about this as really no different as if you just build a class object and then you use prompt engineer and you say, hey, you are a data scientist or you are a tech savvy person. Your name is Lisa, blah, blah, blah. And then you can just talk back to her. So it's kind of like the same idea as that that's built into this package, which is why you can customize it or you can even just ignore the package and then go your own way and then reproduce it. Does that make sense? When you're going through these exercises, which is what I'm envisioning for deliverable 1, is you want to think about how you can build this in your own way. So that's the key for like how do you do deliverable 1 and then how do you use that to build up your deliverable 2. Does that make sense? So I'm going to give you guys a little bit more content. Like for example, I can define something like, let's say I'm going to use my own personal situation as an example. And to do that, you are now defining your own persona, tiny person. So you want to import that function. And once you import that function, you can just define something that's yourself, right? Let's say I'm using my own name, Yiqiao. is a tiny person object. That's the name, Yiqiao. And then let's say this is my age. I'm not 35. I'm just it's a fake age. So define age, and then you can say, hey, define where you're coming from. I'm from China, so that's my nationality. You can also define your occupation. I'm a software engineer, so I'll just say engineer. And then you can even say something a little bit longer. Say professional history is blah blah blah. Like each has been working AI ML space since whatever. So you can do all of that. You just keep running this code again and again and again, so you can define different personality traits onto that persona, or you can add on to it. If you think about this logically, it's no different than if I just write a long prompt in a chat GPT, right? If I'm just write a long prompt and I can have a wrapper function to let somebody else to keep increasing the prompt, right? So you asked a question earlier, like if your API key has constraints or not, right? Then that is definitely related to what's happening here. Obviously, you can't like put a book in here, right? That's not going to happen. This is going to blow up your quota if you put a book in there, right? So something like that is interesting when you think about that design. And then another interesting thing about is when you are designing a persona, you want to give enough information, but you also want to be condensed. Because when you start a two-way conversation, be aware that both of these persona will be counted towards that token size. Does that make sense? Because now it's one call, it's one API call. So here's a persona, we just define it, and then now you kind of want to talk to it. So I'm gonna use this method, and I'm gonna say listen and act. You can say what is software engineer? And then you will just kick off another conversation. And then this each out person, because the persona is defined as an engineer, so presumably he will know much more about an engineer. You can also repeat this by saying something else that's maybe not related to the domain. I have not tried this actually before yet, so I don't know. I don't know what it's gonna say. Tell me about star signs. I don't know what's it gonna say actually. I'm hoping it says a crappy answer because I don't think all engineers know about star signs. But it says something. I think you can probably this is when the debate happens. If the persona is an engineer, does the engineer know about star signs, right? That's a question that in your own exercise you're gonna think about. To what extent is the question that you're asking the persona answerable by the persona, right? That's something that you're gonna have to figure out and have to define that. So in this case, I don't know about you guys, but like me personally, I think like if you're an engineer, and if I'm building a persona just about the engineer, the assumption is probably don't know that much about zodiac sign or whatever star sign. But I think there's like LLM memory in this persona on top of the persona. So I think this answer is probably partially come from that. Does that make sense? So you can certainly think about that. If you want, like this is kind of like on me actually. If I'm designing when I'm defining this persona, look, if I don't want to know the star signs, then you just say it here. Like he only knows about software engineering, he doesn't know anything about star sign or any other topic. Then the answer will be a little bit different. Does that make sense? So be aware of that little intricate detail when you're designing these personas. Okay, so all of this just kind of sounds like an API call to whatever large language model. Maybe it's interesting, maybe it's not. The next few experiments are a little bit more interesting. I'm going to show you how you have two personas talk to each other, and you just act as observer, right? So that's when you need this function called tiny world. So this function here, let me clean this up a little bit. So this function here, tiny world, that's another object that you have to import. Once you import that, you need to, you can then build a mini conversation with 2 or 3 or however many personas to talk to each other. So the way to do that is to define two personas, right? You need two people to have a conversation. So I'm going to do that right now. So let's say John. Who is John? John maybe is 45, and then maybe he's an American person. And then the way I design here is it's a director of a nonprofit organization for homeless shelter. So that's kind of like his job. And then you can say more about his professional experience. And I'm just going to paste it here. Like he's currently serves as director of a nonprofit organization focused on building and maintaining homeless shelters across the United States, something like that. And you can, of course, like make things up based on your own, idea. So I'm going to run this, and then that's my persona number one. Now I'm going to define persona number two, which hopefully, based on my definition, you can kind of see where the conflict could happen. And that's the interesting part is, are you able to simulate these personas that's very realistic to what's going to happen in the real world? Yeah. Do you have a question? Yeah, exactly. So next person, right? Persona number two, Chris, right? So who's Chris? Chris is a bit older, right? 50. And then let's say he's also in the same country. And then in his case, he's a congressman in charge of approving the fund proposals. And then I'm going to provide a bit more information. Say, hey, he served as a congressman for past 15 years. And then as part of his duties, he oversees the evaluation and approval of government funding proposals, things like that. You get the idea, right? So if you don't do anything as of this moment, if I just tell you, hey, there's a John person, there's a Chris person, you put them in one room, let them have a conversation, you can kind of get the idea that they're gonna probably have some sort of conflict somewhere down the road. They may fight, they maybe not. That depends on, like, you need more information than what we're having here. But there's some sort of a conflict, right? One person obviously want money, the other person approves money, so he's gonna ask a bunch of questions. So you can kind of expect, if I put these two people in one room, the conversation is gonna be like, John's gonna ask for something, Chris is gonna ask some other question back because he needs more information to approve the funding. So if you can see that, then this project is gonna make a whole lot of sense with for you. So what I'm gonna do is, where's my kind of one second. I'm trying to find. I'll just go to the package. Hi, come on in. I missed a API somewhere. Hang on one sec. Yeah, there's a conversation API that I missed somewhere that I need to find. Let me see if it's here. I thought I saved it earlier, but for some reason it's not there. Create Lisa. Where did it go? I'm sorry. Let me check the memory of this. So what I'm trying to find is there's a line of code that grab the two persona and then stick them into like one conversation, and then you have to trigger that conversation. Yeah, exactly. All right, let's see. Yeah, that's a good point. Let me check that. Yeah, sorry about that. I thought I saved it somewhere, but yeah. Okay. So it's a better visual. Yeah, define person, and then yeah, this one. Yeah, this one. Thank you. Yeah. Yeah, I thought I saved it somewhere. Okay. So what's gonna happen is you're gonna define a world, and then you're gonna call the tiny world function, and then you can give a name. I'm just gonna say whatever, conference room 1, something like that. And then in this array, you're gonna physically stick the two persona in there. So if it's John, it's John, Chris is Chris. So what we're gonna do is John and Chris. Notice that these are not strings; they are actual tiny person objects. Yeah. So once you define the world, now you can trigger a run. So you say world.run, and then the parenthesis of this number means that how many conversations of back and forth you want to do. 4 means back and forth 4 times. So in the sake of time, I'm just going to do 3 times. And then let me zoom in a little bit while this is running. Oh, yes, I'm so sorry. Let me clean this up. Yeah, I think I missed it. Yeah, I missed this. Thank you. Let's see. So world. No, not world. Let's start with John. Listen. So you want to ask Chris for funding opportunities, something like that. Yes, you're right. So you need a trigger. And then once you have a trigger, then you can hit the world dot run 3 times. I'm hoping this works. There we go. Okay. So in this conference room 1, John is going to start a conversation, say, "Hi, Chris, I want to discuss potential funding opportunities for a homeless shelter. Do you have any leads?" And then once John give Chris that conversation starter, Chris is going to think about it. John's asking about funding opportunities for homeless shelter. I need to recall any recent proposals or leads I might have regarding this. And then he says, "Oh yeah, hi, John. It's great to hear from you. I do have some leads on funding opportunities for homeless shelters. Let's go over them together." And then the conversation continues from there, and then they're probably gonna go through some of the funding together. I mean, this is the first, I'm reading this the first time as you guys are right now. So you kind of you get the idea, right? Once you start a trigger, the two persons gonna carry out a conversation based on the persona, and then you can use this to simulate a conversation within one topic. Does that make sense? Any questions? So here's one particular problem with this package that me personally I found it difficult to use. You can quickly simulate the conversation and it flows perfectly fine. But the issue is if you have numbers in there, and then if something goes wrong, then you're kind of stuck. Like if someone here, someone's talking about a particular number, let's say there's a math problem in there, and then the person starts hallucinate, then guess what? The rest of the conversation is gonna start hallucinate because that previous person started hallucinating. So something like that, you want to be a little bit careful when you're designing your own version. And then right, so that's one downside. The other downside is there isn't really an independent judge over this conversation that can intervene. Does that make sense? The only observer it's us right now. Like we ran the code, we're looking at this code, it's running, and we're looking at this conversation running. But if you saw something in the middle that you don't like, or you're saying, "Oh yeah, that's not realistic at all," then guess what? There's nothing really you can do within the conversation. You kind of have to go back to the source code above and redefine the trigger or redefine the persona, so on and so forth. You have to pretty much rerun everything that I just showed you. Does that make sense? It's not really like in person. Like for example, if you are talking to him, and then you guys are talking about something that, like let's say you guys are discussing a math problem that's wrong, I can then come in here immediately and say, "Oh, okay, stop. That's 1 + 1 it's not 3, it's 2," like something like that. I can stop the conversation immediately. But in this case, not really, right? You can stop the code, but then you have to go back and rerun everything to redefine the persona. So that's another downside. So those are 2 things that for you guys to think about, because I'm hoping for deliverable 1, you can at least reproduce what I did here. Meaning that you can install the package, you can run the package, and then in the submission, if you can show me that you have this script, then you show me that you understood what's going on. And then the second deliverable, of course, we're going to talk about this more, but the second deliverable, the idea is if you can look at the script and say, oh yeah, I don't like that. I want to shut it down. But then I don't have a way of intervening because this package is hard-coded. How do I work around it? So those are two ideas that you can take from deliverable 1 to deliverable 2. There's another idea that I want to throw out there just for you guys to think about. The other idea is how you can connect this with project 1. Project 1 says you have a prompt, and then the chatbot gives you something back, and then you're like rating it, right? We ask function, we design a function, we make API call, we go through all that stuff, right? But what if in reality, what if the real answer is just to ask that person? And that's what this package is doing for you, right? If I'm not a designer, I will have no way of understanding if a reference makes sense. If user asking a question about diamond, right? I will have no way of knowing that. Sure, I can make API call, but API call still has my bias inside of it as an engineer. But what if in the real world, the project 1 can actually be done and simulated using the answer here in project 2? Does that make sense? So I want you guys to think about that when you're going to the first deliverable. And then those ideas will build a gap between two projects, and then also from first deliverable of project 2 and the second deliverable project 2. Does that make sense? Any questions? Okay. One last concept that's very important I want to show you is this thing called a Turing test. So everyone here should know a Turing test. You either know or you don't. It's a very simple concept. So I'm hoping you guys all do, right? So what is a Turing test? Turing test is a test that tests the robot or computer or algorithm's ability to fake a task, right? If an algorithm is able to fake it, then the algorithm is set to pass the Turing test. So the concept is very simple. Let's say there's a person C and there's a person B. So these two are humans. And then in this room here, there's a computer A. And let's presume that these are all independent rooms. You can't see each other. You can't talk to each other. You can't hear anything in there, right? Complete independent rooms. The only thing that's passing from one room to the other, it's this paper of documents. So from A is going to give you a document to C, B is going to give a document to C, and then C is going to judge whether this document comes from a human or a computer. If C is able to tell, okay, this is obviously wrong answer, or this is hallucination, or this doesn't make sense at all, C is able to say that with high confidence that this is a computer, not a person, or vice versa, then the Turing test is failed. If C is unable to tell, if C look at the document and be like, oh yeah, I have no idea. I mean, could be person, could be not. I'm 50-50. If C's answer is that, then it is said that this computer A or algorithm A has passed the Turing test. So you guys with me? Any questions? Great. So this is a very basic concept, and you should know this, right? This is like the definition of AI, right? You should know this. So now let's apply this concept in the project, right? If I show you a paper, I say, hey, look, this is a conversation. I don't tell you if it's a chatbot or LLM or whatever class, right? I literally just show you these two conversations. John's talking to Chris. Hi, Chris, I want to discuss potential funding opportunity. Like, I don't show you anything else. I just show you the conversation. And then Chris says, hi, John, it's great to hear from you. I do have some leads on funding opportunity for homeless shelter. Let's go over them. If I just literally just show you these two sentences in a document, I say, hey, look, are you able to tell if this conversation is happening between two people or two robots? Now, you either have high confidence that they are or not, right? If you don't, you have no idea that this is coming from robot or human, then it is said that this script here has passed the Turing test. Unless you're able to tell, unless you say, hey, look, like, I know Chris, like, absolutely there's no way a software engineer will answer the question like this. I know for sure this persona, or I know for sure this person in this conversation that you show me makes no sense at all. It probably comes from robot. Unless you can say that, then the script failed the Turing test. If you're not able to say that, the script or the algorithm here has passed the Turing test. Does that make sense? So here's the exercise for you guys, right? When you are implementing these conversations, you can of course read it, you can enjoy it, that's up to you. But the thought process here is, if I cover this, if I cover up this, I cover up all these other crap here, I just show you the conversation in its raw form. Are you able to tell if it's coming from a robot or not? And then try to run that Turing test in your head. Any questions? Perfect. Okay, so we're coming up at the clock. It's almost 7, so let's take like a 15-minute break, and then let's come back at before 7:15, and then we'll continue for the other session of the class. So take a break. Okay, so deep learning, there are two packages, right? It's either TensorFlow or Torch. One come from Google, the other one come from Facebook, where now it's called Meta. And then when you develop neural network, it's going to be either those two packages. Me personally, I tend to use TensorFlow a bit more. No particular reason, just because when I started, that's the package I used. But I think today there's might actually be a preference of Torch over TensorFlow. And then I can show you the code a little bit, maybe later in the semester, of how different they are in terms of like when you're adding layers, and then when you do gradient descent, the Torch makes a little bit more sense. Like for example, the API for Torch, if you do gradient descent, literally just like W, right? Let's say weights, you're updating weights. So W is equal to W minus the gradient. It literally just look like that. Whereas for TensorFlow, if you use a TensorFlow gradient tape, it's like W dot assign weights or something. So that logic of gradient descent, like the subtracting, it's gone. So there's a little bit of that translation, go from one package to another. But that's really it. If you're not coding down to that level, you're just adding a layer, you're just using attention API as it is. That's not so much of a difference. Anyhow, so the most important milestone come from 80s. So Yanlo Kun, which you guys should all know him. If you don't, you should. It's this guy. So he wrote a paper in 1988, showing that convolutional neural network can be done. And then at the time he was at Bell Lab. So Bell Lab at the time was kind of like the peak of like all the smart guys are in there. So he pulled that experiment off, and I showed the experiment like I think the first day of the class, that you can basically have a computer take a picture, and then the algorithm will recognize the numbers in the picture. And he showed that experiment successfully in 1988, which is quite early. And then all the way to 90s was when this thing started to take off. And then the first successfully deployed neural network model, it's actually on the bank ATM machine. So they physically pull that off. Like if you deposit a check, you send the check into ATM machine, you'll take a picture of the check, and you'll physically recognize what is the number that you wrote on your check at a really, really high accuracy. Yeah, so that's him. He started the field. I mean, he restarted the field, right? Neural networks, the first paper about neural network came out in the 30s, in the 30s and the 40s, much early. But unfortunately, we don't have a computer back then. So Yanlo Kun started in Bell Labs, partly because Bell Labs has money, right? It's a lab under AT&T, and AT&T is a big company, has money, right? The debate is, had he started in school, like if you rerun the history and then put him in university in 1980s, probably things will be a little bit different. So that's a little caveat. So that's why we start with neural network. So when you learn neural network, there's an easy way and there's a hard way. The easy way is you write out every single neuron of every single mathematical equation. And what that's going to look like is basically this thing in the middle. This thing in the middle, you can probably unpack that a little bit. This summation term, it's nothing but a linear regression model, right? The K is, you can kind of call that like the number of features, like the feature index. Like for example, beta 1 is the coefficient for the first neuron, something like that. And then this HK, you can kind of think about that as a hidden neuron. Most of the textbook out there, notation will be H. You can pretty much call it whatever you want. Some people call it G. G can be like an activation function. Perfectly fine, no problem there. And then when you go from one layer to another, there's nothing you can do except that in that G, you're throwing another summation in there because it's because that neuron now come from another linear regression model, right? So you get the idea from like first equation to the second equation. Really the difference is in this term, which is really just a neuron, now it comes from another summation. And another summation is another linear regression model. So if you're able to see that, then you get the gist of the math, right? That's kind of it. After the dense layer, you're gonna activate each neuron using an activation function. There's more than one activation function, right? The most popular one is sigmoid. Sigmoid is another way of saying you're doing a logistic regression, because sigmoid happen to be this S-shaped curve, and then this S-shaped curve will bound all the numbers in between 0 and 1. So now it's a probability. And then this pretty much allows you to do classification problem, because otherwise the number will be all over places. Another activation function that people like is ReLU. It stands for rectified linear unit. So it's kind of like a zigzag black line here. It takes the same shape as an S-shaped curve in the sense that if it's greater than 0, it'll probably go up. Otherwise, it will just be set as 0. So that's also another reason where the name activation come from. Like you either activate this neuron or you don't. And the activation idea come from you pass the threshold 0, then you take the value as it is, which is why it's a straight line. Otherwise, your default to be 0. Like if you're -2, you're 0. -4, you're also 0. But if you're 2, that's positive number, you're 2 by itself. So you have a linear regression model, and then you activate it using some sort of a nonlinear function, ReLU, sigmoid, so on and so forth. And that's pretty much the neural network model of the 4 pass. So after 4 pass, now you're at the end of the neural network model, and now you need to come back, right? So the way to come back is you need to pick a loss function. And then the most popular loss function is this guy here, least square. Or maybe you heard of a mean square error, that's the same thing. You just divide it by n here. So let me make sure it's, yeah, okay. So once you're all the way to loss function, then that's good to go. Then you're coming back and you do the gradient descent, the back propagation, things like that. Back propagation is basically gradient descent, but you do it iteratively on every layer. That's it. So when people say gradient descent, when people say back propagation, mathematically, they're talking about the same thing. So let me show you this example. This is the famous example that Yan Le Kun put up back in the 80s. You kind of have to know this example, not just because this is a famous example, but also because this example bridges the gap between neural network and convolution neural network. And then you can use this example to quickly pull off a bunch of experiments. Does that make sense? So you kind of have to know this. You can, this data is everywhere now. Like I think scikit-learn has this data, a smaller version. TensorFlow has the data, Torch has the data. So this data is everywhere. So what is the data? This data is handwritten digits, meaning that someone physically wrote down 0, 1, 2, 3, 4, all the way to 9, and then somebody else has to crop the picture and then make the picture kind of like look very nice in a way that the digits stay in the middle of the picture, right? like for example, let me take my pen. Let's say that's my picture frame. And then if I draw a 9 like this, obviously that doesn't work. Right? So that's not how this data work, right? The data is created on purpose so that whatever pattern associated to the label, it's in the center of the picture and it fill up the space of the picture. Does that make sense? So there's a lot of data curation happening here. So that's number one. Number two is the data size is 28 by 28. So this is kind of like you have to know that, right? 28 by 28. So 28 squared is 784. So there are 784 pixels, meaning that there are 784 numbers in that one picture. And these numbers are grayscale, meaning that if there's a stroke in the middle of the digit that's darker in color, then it's darker. So you can kind of think of that as 0, more towards 0. But if everywhere else that's complete blank, then it's closer to 255. And then in terms of grayscale, there's 0 all the way to 255. So including zeros, there are 256 levels. Does that make sense? So if you look at the entire feature space of this data, then guess what? You have 28 times 28 times 256, right? So that's gonna suck if you do a logistic regression. It's A is gonna wait forever, B probably doesn't work. But people have tried this using logistic regression and it doesn't work. You can also do with a gradient boosting machine that gets the performance a little bit better. Random forest a little bit better, and then all the way to neural network, and neural network beats all of them. So that's the original paper, and that's why the original paper is famous. So it pretty much says, hey, here we have a neural network model that you can pretty much have any layer you want. Here's how you train it. And then it doesn't matter who's training it. It doesn't matter how many layers you have. You can always get the performance to be state of the art. State of the art means it beats everybody else at the time. So that's essentially the highlight of that experiment. And then that's why that experiment is famous. So now you kind of get the idea of what's happening in terms of practice and practicing neural network. Now you can kind of like think about it in terms of classification. So now you know how dense layer is passed from feature to loss. At the loss, what's happening at the loss, right? It depends on your task. If your task is classification, then you need to do one-hot encode, because one-hot encode will turn the vector into the same amount of dimensions as the number of classes that you're trying to predict. If it's digit, there are 10 digits, so there are 10 classes. Then in the last layer, you need to have 10 neurons. And then 10 neurons will match the one-hot encoded ground truth, which then is coded to 10 dimensions. So let me unpack that a little bit. So what that means is, let's say you have x, it's a vector x, and a vector x is, let's say 1, 2, 3. There are 3 samples. Each sample is a different label. Label 1, label 2, and label 3. One-hot encode means I'm looking at each vector, and then I'm turning into binary vectors. So 1, it's 1, 0, 0, because the first spot has a number in there. The other ones are zeros. So that's how I'm choosing to code the class 1, right? It doesn't mean it doesn't mean the class 1 is at this particular case, it's a category. It doesn't mean it's like 50% less than 2. Right? It's not a numerical meaning. So class 2, I'm choosing that to be 0, 1, 0. And same goes with class 3. I'm choosing that to be 0, 0, 1. So one-hot encode means you're taking a vector and then you are rewriting it in terms of a binary coding such that the output matrix has same dimension. Now, of course, you can say, yeah, I mean, I don't like that. I'm going to call that 0, 0, 1 and call the third one 0, 1, 0. Fine, you can do that, and you can probably pull that off. Performance will probably be the same if you like calculate exactly the index to be matching exactly same. The 2 has to be 2, 3 has to be 3, and then the position is reversed in the dictionary. Perfectly fine. You're gonna get the same performance. But why would you do that, right? You're better off just do it in order. So once you do that, you can turn any vector into the dimension that match dimension of the last layer of neural network. And that's when the magic happens. So when I say last layer of neural network, this is the picture of a neural network. The input layer, it's x1, x2, all the way to xp. In terms of the actual number, this guy down here, if you are having a picture data that's 28 by 28, right? Then 28 by 28, that's 28 square. Then this last number is 784. So literally, we're talking about a layer of neurons that's 1, 2, 3, 4, all the way down to 784. So there's 784 neurons in the first layer. So that's the input layer. Hidden layer is whatever you want. You want to have 10 neurons, that's up to you. You want to have 5, that's up to you. So the number of neurons goes into hidden layer, up to you. How many hidden layer you want, that's also up to you. You can have 2 layers, 3 layer. If you don't like that, you can have 10 layer. That's up to you. Obviously, there's a trade-off, right? You have too many layers, it's slow, right? If you have 1 layer or 2 layer, then that maybe you don't hit certain performance. Make sense? So those things, unfortunately, there's no math behind it. It's what we call tuning parameter. So you can only figure it out using cross-validation. The last layer has to be dependent on the number of classes that you're trying to predict. If you're predicting 10 classes, the last layer has to be 10. Right? That's the only way that it makes sense. So in this case, you have digits 0, 1, 2, 3, all the way to 9. Count them together, it's 10. So that's why this is 0, this is 1, all the way to 9. So altogether, they're 10. And then if you do this, then the ground truth has to be a dimension of 10, right? So there has to be like if I rewrite the vector this way, like something like this. Actually, let me go the other direction. Let me write like this. Let's say this is a sample 1. Let's say sample 1 is digit 0. It's the first class. Then the first spot is 1. And then there are like 9 zeros behind. So 0, 0, 0, 0, 0, 0, 0, 0, 0. Does that make sense? So that's one sample. So this guy is digit 0. So quotation mark 0. So that's what one hot encode will do to that label 0. Does that make sense? Any questions? Yes. Mhm. Yeah, that's a good question. So if your problem, you can rewrite this problem, right? You can say instead of classifying 0, 1, 2, all the way to 9, I'm building a different classifier that's, say, digit greater than 7 or not. So in that case, you are talking about a problem statement that's like this: y is greater equal to 7 or not. Then in that case, you have two classes. You're either greater than 7 or not, right? So if that's the case, then you have to scratch this, and you scratch this. In that case, let me use a different color so we can differentiate. In that case, you just have 2 neurons. So like this. And then you look at the first sample. First sample is 0. 0, it's not greater than 7. So it's going to be 0, 1. So you're going to write this vector like this guy on the right-hand side. So now it's a 2-class classification. And then this class here means it's not, it fails this condition. So yes, you can do that perfectly fine. And you're allowed to do that. It's up to you. Yeah. So another thing that I can tell you in industry, what people do is you can build a neural network that's 10 classes that recognize all the digits. And then what's going to happen is there's a digit that you got wrong. And if you get a digit wrong, then you have like a second neural network in your toolbox that's just to predict that digit or not. Like let's say digit 7, you get it wrong based off this first neural network. You have a second neural network that you can then train just on digit 7. And then you can pass that sample to the second neural network again to see if this is the same answer or not. So you can do that. So that kind of answers your question, because then we're talking about same data, but different labels. Yeah. So that's a good question. Any other question? Cool. Let me get rid of a drawing. Okay. So earlier when we talked about logistic regression, we talked about the cross entropy. Cross entropy, it's I think in physics they call it energy function, but really it's the same thing. So cross entropy takes this form. You don't need to memorize the summation thing. Summation thing is kind of like just like a notation. The trick is this y and this log. And then I think earlier in the session we talked about this log function that's going down, right? So I don't want to repeat that example, but here the trick is to understand this y and this log thing is dependent on sample, and it's also dependent on class. So the y is always a ground truth, and inside of the logarithm it's a prediction, meaning whatever come out of the function, right? That's why here it's the function of the input feature x. So in terms of what question that you're trying to predict in the neural network model, it really comes down to two forms. If you have one neuron in the end, that's a regression problem. You're predicting one number, and that number can be pretty much anything on a real line. Or you are doing a classification problem. Classification problem means, end of the day, I have to tell you, 10% of chance class 1, 90% chance class 2. Okay, I'm going to guess class 2. So that will be a more deterministic approach. And the downside of that is, well, too bad. Now you're talking about 2 class. And 2 class is pretty fine. If tomorrow someone else says there's a 3rd class, then that model doesn't work. You have to retrain. Different problems have different loss functions. This is the first one, the least square, that's the regression problem. The second one is the classification problem. So the log is a giveaway. If there is a log, then that's a classification problem. If there's just not, it's a regression. Okay, now I'm gonna try to go as fast as I can in regards to the topic. That pretty much is everything you know about the neural network. Now you need to do make a different assumption of a data set. So earlier we talked about handwritten digits. Handwritten digits is picture data. But unfortunately, when we build neural network model, we're not really taking the picture into consideration. We're assuming that these features, 20 by 28, it's given to us in front of us completely randomly. It's like a jigsaw puzzle is scattered on a table. I have no way of putting those features together. I have no idea, right? I'm not making any assumptions of what data look like. I'm taking all those features, shove it into a neural network, and just pray, right? Fingers crossed. This next family of model is called convolutional neural network model. It's going to challenge that assumption a little bit more, right? Now it's saying, hey, look, pictures are pictures, and the pixels should have a relationship with each other. And that's a correct way of challenging the first data, the first model. So this is a very intuitive way of understanding what that assumption means, right? If you are giving me a jigsaw puzzle and I don't do anything, I just take the entire puzzle, shove into a neural network, then you are pretty much ignoring everything on this picture. And that's a problem. So what convolutional neural network is saying is, look, if you're giving me a picture, that means the pixel means something. And if the pixels are closer to each other, then why don't we use that as a feature? And that's a correct assumption, that you should challenge the neural network like that. So what that means is, let's say you have a face of a tiger. When human look at a tiger, you're not looking at a dot on the tiger and say, yeah, that dot is yellow color, therefore it's a tiger. Right? That's not how your brain works. You're gonna say, oh yeah, I know it's a tiger because it's eyes, because it's mouth, because it's ears. That's how human beings think about these things, right? So immediately you can now go from label and you can move back in terms of feature. So when I tell you tiger, you're gonna imagine the eyes look like that. You're gonna imagine the mouth look like that. You're gonna imagine the ears look like that. Well, that's great, right? But where those ears, eyes come from? Those ears, eyes come from a bunch of different numbers put together such that it looks like that curve, right? So if I may, I can probably zoom in a little bit to this feature here. Let's say ear. Where's my pen? Here. Um, let's say this is the ear. That's the feature that tells me this is a tiger, right? And then guess what? That ear can be broken down to this feature and this feature. Maybe it's a curve. And then a curve can like go different orientation, right? Like it can be this way, and then if you flip it, it can also be this way. Both make sense, right? Maybe what defines the ear is a color, right? Then there's something here that's a color. Makes sense. That's fine. So these things are coming from part of the picture, right? So that's why, let me grab the drawing. So that's why if you scroll down, I'm hoping I draw this correctly. So I think this thing probably come from here, and then this part I think come from here. Does that make sense? So convolution neural network is a mathematical approach to do exactly that. Okay, so now let's take a look how to do that. Um, wait. Okay. Wait. Okay. So there's a statistical function called convolution. And a convolution function is essentially to mesh two functions together, right? So this is actually the easier way to understand it. Let me show you another visualization. Let's go to our class repo, and then I think I have another visualization here in deep learning. Here. So mathematically speaking, what is a convolution? So convolution takes two function as input, and then it produces a new function, right? For example, I have two functions, f and g. F looks like this, and then g looks like this. You can loosely translate to there's a square and there's a triangle. So convolve, when you convolve two functions together, means that you're combining two of its features. And then what happens when you roll this orange function over to the blue function? You get the basically the best of both worlds. Not necessarily best, but just like the gist of both worlds. So it's gonna look something like this. It's gonna partially look like this purple line. Does that kind of make sense? So when you're convolving one function with another, mathematically you're essentially doing this. And then let me see. I have a formula. Oh, I don't have formula. That's okay. Now let me show you the discretized way. So if you have two functions that's continuous, then that's what I just showed you before. But in picture, you're not going to get a continuous data because picture, the pixel level are cut in terms of threshold, in terms of brightness. You're always going to find an integer somewhere. It's not going to be a continuous line, right? So that allows you to essentially use matrix. So that's what this idea come from. So how does convolution work? You have your original matrix, A, B, C, D, F, G, something like that. And then you have a filter, let's say alpha, beta, gamma, and delta. So how it works is you are putting this filter on the top left corner of the picture and just do this rolling motion. So let me grab my pen. Let's say this is your filter, alpha, beta, gamma, delta. So how it starts is you start from top left corner of the original picture. And then what you're going to do is you're doing a dot product. So dot product means you're taking A and then you multiply by alpha. So A times alpha plus B times beta. So B times beta. Now you guys get the idea, right? Same goes with the next pixel is D times gamma plus the last one is E times delta. Does that make sense? So this formula here is called convolution. And then once you finish that, you just put that here. And then that's the first number of the new picture. And then after that, you're done with row one, column one. This is row one, column one. So once you're done with that, you move right one column. So you move this over right one column. And then what that means is this purple box, let me clean this up a little bit. So what that means is that purple box now has gone here. Does that make sense? And then you're doing the same thing, dot product, add everything together. So the next number is B times alpha plus C times beta plus E times gamma and plus F times delta. Yeah. And this guy is the convolution for the second the second number of the new picture. And then you just put that here. Any questions? Okay, great. So if you understand that, then here's a question. Why do I have to move exactly one column? And the answer is no, we don't. If a picture gets very large, you can move two columns at once if you want. You can do that. You can move three columns if you want. But then here's the problem. If you move three columns, then does that mean that you're skipping one in the middle? And if you're doing that, then you better have a good way of arguing why that's a better approach. Does that make sense? So typically what people do is they want the algorithm to be fast. So they skip like 2, 3, 4, 5, whatever, right? But then if you're gonna do that, then guess what? Your filter also has to be large accordingly so that it covers enough columns so you're not skipping any features. So in other words, what people tend to do is if you're gonna skip more like this, if you're gonna do that, then make sure this matrix also gets bigger and bigger. Otherwise, you're losing information. Like there are parts of the picture that you're not touching. Does that make sense? So that's one thing. Another thing is, and this is when things get really interesting. Another thing is, if you look at this algorithm at the face value, it reduces the dimension very fast, right? Here, the original picture is 4 by 3 because there are 4 rows and 3 columns. But then once you do this convolution filter once, and when I say once, I'm talking about filter that's 2 by 2. So this guy is 2 by 2. And then you're skipping one column, you're skipping one row. And then once you go through that once, you get a new picture that's 3 by 3. Oh, I'm sorry, 3 by 2. Here. Yeah. So in other words, you're dropping your features from 12 to 6. So that's 50% reduction. So this way you're gonna, like, imagine you have 10 layers, you're gonna, like, you won't even do 10 layers, right? Because somewhere down the road, your feature is gonna be gone. It's gonna be one number in the end, right? So you also don't want to do that because that's overkilling that, right? So that's one thing. Another thing that people don't really use is the reverse convolution. And this is when things get really interesting. Reverse convolution depends on task. When you want to increase the resolution of original picture, let's say this original picture is 4:3. Let's say 4:3 is not 4K. It's like some crappy camera, like video taken 50 years ago, right? You want to take that video and enhance the resolution so that it's like standard 4K today. You can do that. It's called reverse convolution. Reverse convolution means you're doing the exact same thing that we're talking about here, but you're expanding up and left. Instead of going right and down, you're going up and left. So how it works is, I have to get rid of some of these drawings. So how it works is this. Instead of having a filter go this way and then go this way, now you're having the filter. I'm going to use a different pen. Okay, now you're going this way and then this way. And then people are like, well, wait a sec, I don't have numbers there. Well, that's true, you don't. So if you don't have numbers, then guess what? When you're moving to the left, let's say you're moving left one column, it is correct, you don't have two numbers here. So when that happens, it's you can either swap it or you can replace with one. Let me rephrase that. You can either use 0 or replace it with 1, meaning that you have a choice to make. If it's 0, let's say if it's 0, 0, then you're left with AD, beta, and gamma. Then the neural network is going to learn how to make that a new pixel such that it increases the resolution. So that's one thing that people can do. Another thing to notice in response to that is, if you're going to do this, then the final layer needs to be a picture. So probably not today, but somewhere down the road, I'm going to talk about this thing called UNet. UNet does exactly the same thing. So it increases the resolution. And then there are a bunch of other projects in the industry that take some old footage and increase the dimension. It's using the same strategy. Awesome. Let me erase the drawing and then. Any questions about this? Good. Okay. Couple more tricks to tell you guys. It's kind of basic at this point, but it helps out on avoiding overfitting and things like that. Max pooling. Max pooling, it's very simple, as what the name suggests. Take the maximum number. For example, how this works is if you let's say you do non-overlapping 2x2. So that's the filter that you're using, non-overlapping 2x2. So what that means is you start from top left, and I give you 4 number because 2x2. You take the maximum number of that. So if it's 3, then it gives you 3. So that's why this new matrix, top left corner is 3. And then since we're talking about non-overlapping, then you're not moving one column, right? You're moving 2 columns to the right because you don't want overlap. So the next spot on the picture, it's actually here, right? You don't want overlap, right? And then you take the maximum number. So then that's going to be 5. Then that's why this is a 5. Make sense? And same thing here, here. That's why you get 2 and 4. So that's it for max pooling. Using everything that we just said above, convolution and max pooling, it turned out that you can actually repeat that a couple of times. And then guess what? If you repeat that a couple more times, you reduce the dimension. And then if you reduce dimension enough, then you can combine that with dense layers, which is the original neural network model. And neural network model can learn what the pattern is from those features to the final label. And the final label can be like 10 classes, then it's 10 classes. It can even be 100 classes. I think the CFAR 10, the CFAR data set has 100 class. I think it's like a CFAR 1000 or something. Like there's like a class that's a data set that's like 1,000 classes, and you can get those to work perfectly fine, like high accuracy. Okay, so I'm gonna let's take a break. It's coming up to an hour. Let's take a break and then let's come back and then let's kill a few more slides and then we'll call it a day. Any questions? Awesome. So let's take a break. Let's come back in 8:13. Okay. So what that means is after convolution neural network model come out, there's like a whole list of models that comes out after that. That's all based on different variations of convolution neural network. Okay. So we're gonna talk about some of them that's very famous, that pretty much you can just one line of code from TensorFlow or Torch, you can call that model. So first one is LeNet, second one is VGG, and then we're going to talk about RaiseNet, DenseNet, and then Inception. And it actually goes in that order. So here's the logic of why each one and how each one is designed. Start with LeNet. LeNet is actually by Yan LeCun. The link of the paper, let me hide this. The link of the paper is here if you want to read it. So very simple design. There's convolution and there's pooling. And then you just rotate that 2-3 times. That's kind of it. After that, the features get reduced from the dimension of the original image, and then you concatenate it with, not concatenate, you combine with the dense layer afterwards. What that means, it's very simple. What that means is, hey, the original data or image data, let's make one more assumption, which is the pixel now have to do something together. And what's the math to make that happen? Convolution. That's all they're saying. So if you can accept that, then why don't we do that 5 more times? And turn out that's another paper. So from let me use my So from LeNet 5 to VG16, there's no novelty in terms of math. It's just a matter of how many repetitions that you're doing in terms of the convolutional layer. Any questions? Okay, so now here's the thing. If you can repeat 3 times and now you repeat 5 times, and then it turns out performance better, then the problem is, what if you just keep going like 10 times, 20 times, 30 times, right? Well, 2 problems. One, you don't have enough dimension to go by because every time you do it, the dimension drops. So you can't do it infinitely. That's number one. So then people are like, oh, why don't we just, have like an image data that's like 4K or something? Then you can do like a million layers, right? It turned out that doesn't work either because end of the day, you're going to overfit. So that's why this paper proposes concept called RaiseNet. RaiseNet is based on residual layer, this thing is called a residual block. So what a residual block is talking about is whatever feature comes in, we're gonna make two assumptions. One is some of the features is gonna be important. Some of the features it's not gonna be important, but it doesn't say which is which. So that's the trick about this. So how it works is this: you take your output from your previous layer, and then you make a duplication. And then that duplication, you're gonna skip over whatever dense layer in the middle, and then that duplication, you're gonna move that 2 layers down the road. And concatenate that with whatever it is that come out of those 2 layers. So now, why on earth do you want to do that? Well, it turned out, here's the interesting thing. Imagine you're studying for an exam, right? If I'm giving you like a book of chapters to study, there's going to be chapters that you already know. You don't want to spend too much time on that. There's going to be chapters you don't know. You want to spend time on that. So it is up to you to figure that out. But end of the day, you're not going to spend the same amount of time on every single chapter because there are chapters you know better than the other. So that's what's happening here. It's given neural network that capability to make that choice if there's something come out of X that you want to put more weight on or not. So this design gives neural network that choice. So if you read that paper, it turned out it's a very interesting performance. If you so this is the performance that they talk about in figure 1 in the paper. So on the left-hand side, it's a training error. On the right-hand side is test error. So it turned out that if you just infinitely add layer, like let's say you're at 20 layer, you're gonna add to 56 layer, and you're like, fingers crossed, I'm hoping this neural network is gonna learn all that it's gonna learn. Well, it turned out that's not true because the performance actually drops. The error rate goes up. How do I know that? How do I know that? Well, the red line is above the green line. So that's a problem. So that's the problem that the paper will say it's a problem. So now you go back down. It proposed this new design, which is design aside. Now you can then take a look at their performance. It turned out what they're saying is, if you now have this design and you allow neural network the capability of making that choice, what to learn and what not to learn, then you can feel free to keep adding the layers. And if you add the layers, then guess what? The error is going to get better. Does that make sense? So that's kind of like the proposal of what they're doing, of what they're talking about. So let's see. This guy on the right-hand side, it starts with an 18 layer. If you add to 34 layer, they've shown that the red line, which is the layer with the model with more layers, now the error is smaller. So then that gives them a paper. And then it turned out that you can actually repeat this thing many times. If you repeat many times, it'll give you a picture like this. Does that make sense? So you just every 2 layer, just skip it, just like that. So now here's the thing. If you can do that, and if you accept that will give you better performance, then I can do whatever I want, right? Like I can, like why do I have to skip twice? I mean, I can skip here and then here and then here. Well, why don't I just skip every layer? Right? Why don't we just go crazy on this skipping thing? And that's true. It turned out that's another paper, and people do that, and that's another paper that people do, and then they show better performance by skipping more than one time. Because 2 is kind of like arbitrary, right? Why 2? It makes no sense. Why do you want to do 2? If you can accept 2, you should do 1, 2, 3, 4, 5. So that's interesting. And then it turned out that people are still not happy with that. And then if you're gonna accept this, if you can skip 1, 2, 1, 2, 3, 4, 5, like anytime you want, then why don't you start doing branches? Yeah, I mean, you already opened that door. The door is open now. Like, you know, why do you have to skip? Why can't I just go sideways? And then people do that. And if you do sideways, that gives you another model called inception. And that's the inception module. So it goes sideways, and then when it goes sideways, it uses different configuration for the convolution layer. So for example, if you go sideways here, you can use a filter that's 1 by 1. If you go down here, you can use a filter 3 by 3, 5 by 5, so on and so forth. You're gonna concatenate them in the end anyway, and then your network can learn which one's good, which one's bad. So that's the idea. So that gives you inception, which is the last model here. This guy here, it's called DenseNet. And this is the full architecture of an inception model. And then it's before attention layer come out, this is the best one. And then attention layer came out and changed everything. Okay, that's it. I'm gonna stop here, and then I'm gonna let you guys think on those projections and think on that. And then yeah, just wanna wrap up today's session by saying you should get a feeling that you can do whatever you want in terms of design of the neural network model. You can have however many layers you want, however many neurons you want, and you can go up, down, left, right. You can go whatever direction you want, and you can concat them in the end, and you can make however many predictions you want based on any class that you want. Any questions? Awesome. Okay, let's stop here, and then yeah. So next week no class. Next week spring break, and I'll see you guys into the last week of this month. Make sense? Um, Let me type that out. That would be the first deliverable. I'm expecting the first deliverable to be like a script of the tiny troop conversation. So I'm gonna type that out and send that in a course announcement. But if you're able to install that package and run through the code and generate some sort of conversation, and then submit that as a markdown file in your repo, and that's good. Yeah, good question. Any other question? Good, awesome. You all set?